All right, welcome to the final session of the day on tissue folding. I'm Priyom. I was a graduate student with James a couple of years ago now, and I played around with the FPP plugin a lot during my PhD. So I can share some more capabilities from it, both from an XML and Python perspective, and how you can sort of manipulate the link properties in space and time to sort of mimic biological phenomena. And so I'll start with an overview of what we are going to cover today. And so you can maybe decide what's most helpful to you, because the first part of building an epithelium, you have already seen most pieces of it. So the idea is that we will be using the same simulation that Julio is using to build compartmentalized cells, which is sitting on an ECM layer. And our eventual goal will be to put focal point plasticity links between the apical compartments of this epithelial layer and sort of try to fold the tissue. And then the next three sections of this module, we will mostly be dealing with Python scripts. So how to manipulate more focal point plasticity properties using using Python, and we're going to look in the context of segmentation, or how we can break down an epithelial layer into discrete chunks. But the general concepts of what we'll be using in the scripts, from breaking links, creating links at specific time points or in specific locations, might be applicable to whatever biological process that you study. Okay, so to sort of start us off, I'll tell you about sort of the, very incredible examples of tissue folding in biology, which is where you maybe can start off with a flat layer of sheets, but during the process of development, that sheet undergoes rapid tissue shape changes to invaginate or develop folds. Uh, these processes oftentimes help in the repositioning of cells and becomes very relevant, for example, in gastrulation, where you need the process of invagination to separate the three-germ band layers, which will take special fates later on during development. So tissue folding is, a very nice phenomenon, and it would be also great if we are able to replicate that in CompuCell3D. So what actually generates tissue folds, or what do we need to focus on to be able to manipulate these tissue shapes? So that comes from trying to understand a bit more of the cellular behavior, because the cells which build up tissues oftentimes will be comprised of intricate elements of cytoskeleton, which can exert forces on neighboring cells to basically change the shape, and to change the shape at the cellular level, which will then be imparted at a tissue level. So, for example, if you look on your left, this shows an example of a columnar layer of cells, and there is some increase of contractility on the apical side, which sort of changes the cell's shape from a columnar to a wedge shape, and eventually this will imprint like a folded shape in the entire tissue. You can also have other examples as shown in the middle here, where if you want to expel sort of this necrotic cell out of the tissue, you can change the cell behavior on either side and sort of either elongate or increase contractility between the two neighboring cells on either side to sort of be able to expel that cell out. So all of these sort of requires a basic understanding of how cells itself, how we can model cell shapes and use them to sort of change tissue properties at a more global level. And so our goal for this session will be to start off with mostly a columnar epithelium and sort of be able to increase contractility on the apical side of the tissue layer and sort of bring it to a more folded shape. And like I said, you might have already seen the basic code for the basic code for building the epithelium. But if you would like to look at it again, it's all the codes for the session has been uploaded under the demos folder. And if you look at module_7_3, you should be able to find the 5 different codes that we'll be using. For the first part, the code should be in module_7_3_1. And so that code relates to the first building of the epithelium and basically just putting links between the apical surface. So let's start with that. And I'm going to be monitoring the chat. So if this is something that you know it's too fast or too slow, or you have questions, feel free to write them in the chat, and I'll to answer them. Okay, so these are basically these steps through which we're building the simulation. So we're going to basically generate 4 different types of cell types: apical, lateral, basal, and ECM. We're going to be putting them in a more like a columnar fashion in the simulation space. You can pick these parameters to begin with. You can also play with the size of the simulation or the size of the cells itself. We do need to add the focal point plasticity plugin, which you probably have seen yesterday and today as well. And then for the first 2 sections of this, we'll be using the uniform initializer to sort of build our tissue layer. And then we will start with modifying some of the FBB properties in the XML, but then we will migrate to a Python steppable file so that we're able to manipulate some of these properties a little more. And in the XML file, make sure that our contact energies are adjusted enough so that it mimics the compartmental cells that we've been looking at. All right. So to start us off, if you're following along with this, these are the steps. And if you're not following along, feel free to download the first codes of this module. All right, so the dimensions of the simulation that I've chosen are 350 along the x-axis and then 100 along the y-axis. Feel free to keep them as it is for now. And then I have chosen periodic boundary conditions. In the later simulations, we will be playing around a bit with actually fixing cells in the simulation itself. But for now, we can keep it at periodic. And the other parameters can be kept the same as of now. We are going to add 4 basic cell types here. So apical, lateral, basal, and ECM. And we're going to sort of ignore the chemical field window, but make sure that focal point plasticity is uploaded at the moment. The other plugins that are of interest to us are ContactInternal, Volume Flex, Cell Neighbors, and Center of Mass, which will probably be already checked. Okay, so these are all the basic ingredients of our simulation so far. And then if you have put these plugins in, and with just this, without making any further changes, if you run this on CompuCell, you should be able to see a simulation that covers basically some part of your grid, but will show a mixture of all of these different cell types. Because right now we haven't fixed any properties on where these cells are to be placed. So you should be able to see this by now. So like I said, our next step is going to be designing an epithelial monolayer. So we want to be able to sort of specify the exact regions over which these different cells are going to be placed. And so we will be following the same sort of schemes that Julio was following yesterday. But our basic motivation for that is the following. A cell body, an epithelial cell itself, it's a very complex structure, and depending upon if you just like migrate, if you just look at different regions of the cell, you'd be able to see presence of different junctional structures. Closer to the ECM side, the epithelial cell might have integrins that it uses to connect to the membrane or the basement membrane. And on the apical side, you might see projections like microvilli, which are like towards away from the epithelial cell surface. So to make sure we follow or understand this architecture of the epithelial cell, the best way that we can represent this in CompuCell is by using the idea of compartmentalized cells, where different compartments represent these different phases or regions of the epithelial cell. So this is the structure that we are going to try to do. And so we're going to try to place an ECM layer at the bottom. Then we're going to try to put a basal layer on top of it, then a lateral body, and followed by the apical cell. So to set up these properties, you can go to the XML file, and you can pick up the sizes that I have for the simulation. You can also feel free to play around with your own. So the idea is that we're going to build the first layer, which is the ECM layer, and you can specify from 0 to 35 on the y-axis here. And we could specify the width of each of these ECM cells to be 35. And make sure that in this block only the ECM cell type is specified. Otherwise, it will try to fit more cell types within that region. So this is our basal ECM layer. The next step we're going to follow is trying to add up the basal compartments. And so what we're going to do is we can copy the same block that we used for the ECM cell type. We can just duplicate that. The only difference is that now we need to extend the y-axis from 35 to 42, where I have taken a cell size of 7 by 7, but feel free to mess around with that as well. So now once we have specified the next layer closest to the ECM, make sure to change the cell type here to basal. And then we're going to just replicate the step for doing the lateral layer, which is going to go from 42 to 49. And then we're going to do the apical layer, which is going to go from 49 to 56. So if with just these basic steps, you run the simulation, you should be able to see at least, and if you have checked on that the focal point plasticity link should be visible, you should be able to see a bunch of white lines between your cell types. To make sure your ECM cells do not disappear or shrink, if you can go to the volume plugin and set the target volume to 1225, then you should be able to see the correct dimension of what you specified these ECM cells to be at. And so you should be able to see something like this. I'm going to just pause for a moment to check if people are following along, or if you have a simulation of this sort. So Troy has a question on where the apical and lateral cells initialized yet? Yes. So let me go back one slide. So if you go back here, so what you can do is you can just duplicate the same chunk of code that was used to create the ECM and the basal layer. And then you could just duplicate it and then substitute it by the type of lateral or apical. And just make sure that the Y positions at which you're placing these cell bodies are different from each other. So for example, the lateral will go from 42 to 49, while the apical compartments will go from 49 to 56. And you can play with your own percentages, and eventually you can also check how the focal point plasticity plugins have to be adjusted to incorporate that differences in volumes. Right. So then, yes, the next step, yeah, don't forget to make sure the ECM volumes are correct in the volume plugin. And once you set the target volumes correctly, you should be able to see something where you have your layer and your volumes have been initialized correctly now, but the focal point plasticity links will probably be all over the place because we haven't done anything with them yet. All right. So now that we have this, I mean, we have created some semblance of an epithelial layer, but we need to be able to be in more control of these focal point plasticity parameters. And remember, our goal is also to be able to induce specific forces so that we're able to bend or induce folds in this tissue layer. So to be able to do this, we are going to ignore a lot of the other focal point plasticity links between all the other compartments, and we're going to only focus between the apical compartments. So just as a reminder, Julia went through this yesterday, but basically the parameters of the plugin that we'll be playing with it are the lambda, which basically tells you how strongly two cell bodies pull on each other. This activation energy term lets us add a term so that it helps in the generation of these links. So helps overcome the other Hamiltonians that you have already put in, and makes it more favorable for a particular link to be created. For now, we can keep it at -50 in the simulation, and we won't be messing around with it. But feel free to check what happens as you reduce or increase this value. The target distance is basically the desired target distance between two cells, while the maximum distance sets a cutoff for what the maximum link distance the focal point the FPP could be created over. The maximum number of junctions that basically tells you how many number of neighbors each of these cells could connect with, how many number of links each cell could form. And then the neighbor order sort of like specifies, even if your cells are not, for example, touching, over how many cell neighbor orders this could form, the link could be formed. So we'll be using some of these features to basically induce forces along the apical direction. But as a first step, let's make sure that we delete all of the other links between all of the other compartments, apart from the apical to apical compartment. So any internal or any external links apart from apical to apical, external, feel free to remove them. Also, don't forget to uncomment this local tag. This will help us later on as we try to modify some of these FPV properties in the Python steppable file. So if you don't uncomment this, you will not be able to do it. You'll not be able to do it from these steppables. So yeah, what we're doing at this stage is sort of like deleting all the other FPP links between all the other compartments. And so at the end, what our FPP tags should look like is this. So we have the focal point plasticity, make sure we have uncommented the local tag, and then our FPP links should be created only between apical to apical cells. And so if you're following along and generating a simulation with me, you should be able to see, if you just step through the simulation, this is what you should be able to see. Because we have only specified max number of junction at 1, you'll be able to see some cells have links between their neighbors, while the others do not. And you should be able to see links only between the apical side of the tissue. Then we're going to do actually two more things in the XML file before moving on to the steppable. But the first thing is, let's set all of these parameters to be 0 in the XML file. It's because we want to create new properties for all of the FPP links, and we'll be doing it in the steppables. So apart from the activation energy, which we're not going to play around with much, make sure that all of these other parameters are set to 0. And this without any, with the maximum of junctions to 0, the target distance to 0, the lambda to 0, you should now see that the links have all disappeared. And this will provide like a good setting for us to manipulate some of these properties in the steppable. The other thing we have to also keep in mind is, because these are compartmental cells, we have to make sure that we have a correct hierarchy for their internal and external contact energies. So what we want for within the cell itself, we want something so that the cell compartments do not fragment and mix amongst each other. So there's some definition of the compartments as being separate, but you don't want the contact energies, the internal contact energies, to be so high that the cell itself, cell gets divided into 3 different chunks. So you want them to be on the lowish side. So this is what I have for the code and for this, but feel free to play around with your own hierarchies of contact energies as well. So apart from the internal, like apical to apical itself, or lateral to lateral, or basal to basal itself, the intercompartmental, like apical to lateral, or apical to basal, or basal to lateral, have been all set at 2. That's the number that I have used. And then for the external, if you go back to our picture of the cell sitting on the ECM layer, we want the basal layer to sort of like being next to the ECM layer. So we want to set that contact energy to be on the lower side. We want the apical contact energy, the apical surface, to be facing towards the medium. So we again want that contact energy to be on the lower side. We want the apical compartments between cells to be next to each other. The same for the lateral and lateral of 2 different cells to be next to each other, and similarly for basal to basal. So all of those across these cells, those energies have been set to be set to on a lower side, but you definitely don't want the basal side of the cell exposed to the medium. So you want that contact energy to be super high, or you don't want that apical side to come back and be close to the ECM. So that contact energy has been set as high. So this is again a hierarchy that you could follow, but feel free to pick up your own parameters as well here. This is what I have. I'm going to just pause for a second if you want to copy any of these values. So basically for the lowish values, I've picked 5. For the most extreme values, I've picked 20. and for the intermediate values I've picked in. And so if you sort of now run the simulation before going to the steppable file, you should be able to see a layer which is more or less in place. If you basically set the ECM to ECM contact interface to be 0, you'll be able to see all the ECM cells are sort of like mixing with fragmented cell boundaries. And the links in the simulation should have disappeared at this point. We have the first screenshot from Harini. That looks great. We have another simulation from Ronak. That looks great too. So now what we're going to do is go to the steppable file. You should be familiar with the steppable file at this point, but in your Twit editor, if you click on the module 7_3_1 steppable.py, this is where we'll be making most of our changes. Okay. So the first thing that we're going to be doing is the following. So right now we have created the illusion of an epithelial layer, but within all of these cell types that we have created, they sort of don't know yet that they're part of the same cell body. And they won't know this until we are able to connect the apical, lateral, and the basal compartments together. So the step that we're going to achieve this is the following. We can take one cell type. It could be either apical, lateral, or basal. Once we have identified that particular cell type, we're going to find the center of masses of the other cells that exactly line up in the y direction with that apical cell compartment, for example. Once we have identified that these 3 cells have been created in very close proximity to each other, that's how we had created our simulation. Let's now assign their cluster IDs to each other's. So right now, for example, if I pick up the cell type to be apical, what I would do in the next couple of loops is go through all of the lateral cell types, which exactly have the same X position, which exactly have lined up along the x-axis, but are only differing in the position of where they're located along the y-axis. So if there's center of mass on the x-axis have aligned, I know that I'm meant to create them to be part of the same cell. So then I can reassign cluster ID of that new identified cell to whatever cell I have to whatever cell I was looping on over here. And I can follow the same procedure for the lateral cell type and for the basal cell type. I believe you have seen the reassigned cluster ID so far, but if not, let me know and I can go over it again. This sort of the reassignment of the cluster IDs helps to connect these different cells as being part of the overall cell body. Okay. The next thing we're going to also do here is, okay, thank you, Seema, for letting me know that it was done before. That's very helpful. So the other thing we have to do now is now we have assigned, we have built up our compartmental cells, but we now need to form specific links only on the apical side, because those are the properties that we'll be playing on in a bit to induce specific forces. So the way that we do this is in the next couple of lines, we're going to go and visit all the cells of the apical subkind. Then we're going to find all of its neighbors. So any connecting, any neighbor that it shares a common surface area with for each of these cells. We're going to first make sure that the neighbor identified is also of the subtype apical. Once we have done these steps, we are ready to form a link between the apical types. So this is what that whole chunk looks like. So yeah, so the steps that we did in the steppable, we did two things. We first made sure that our compartmental cells have been initialized to the same cell body. And after that, we had made sure that we loop through all the apical cells. We have identified which are their neighbors based on contact surface, based on connecting surfaces. And then we have formed links connecting the two apical cells. So if you follow these steps, or even if you are looking at the code on the XML file, this should be in lines. If you go to the steppable file, all of these pieces of code should be in from lines 14 to 31. So with this, if you now set the simulation, you should be able to see perfect, yeah? So now Anastasia shared her screenshot, so you can now see links on the apical side. I would check some of your contact energies, Anastasia. It might, just seeing the level of mixing, it tells me that maybe the yellow to pink contact energies might have been a little low. That's allowing you to mix and fragment it that way. So yeah, maybe check that out. Okay, but perfect. So if you all are on the same page right now, this is basically our first step in being able to in being able to couple the cells being able to couple the cells through links. So Anastasia's comment is even if the energies are same, she's getting a lot of mixing. That'd be interesting. The other parameter I can think of would be the temperature. The volume would also matter if we have the same focal point plasticity parameters, but different sizes of the volume compartments. So those are the two factors that come to my mind. So there's another question on what does the if neighbor line do? Okay, right. So this is just an extra precaution. Because we're making all of these changes in the start function, right? Before before the simulation has even proceeded, allowing the cells to move around or do anything else. But we want to make sure that the links are only between the apical to apical neighbors. So the question, so the if neighbor type equals apical, make sure checks that the cell is of the same kind. But I just realized that you're also possibly asking about the other line, which is if neighbor on its own. So that line makes sure that your cell type is not medium, because whenever you whenever you use this syntax of get cell neighbor data list, it's also going to return it's also going to return medium cells. So if neighbor allows you to pick away the cells that are not medium. And in the Python syntax, the neighbor, so I believe the value assigned to the medium neighbor cells is 0. So if neighbor lets you eliminate any values which are 0. Okay, so that's the basic simulation. So now we're going to go to the next step of this module, which is trying to specify features that allows us to fold this tissue. And I wonder if you guys have any ideas on how we might do this already. So our goal is, given this epithelium tissue layer, how can we sort of fold this tissue at a particular location? And what features of the focal point plasticity plugin could we use to achieve that? So I'm going to just pause for a second to let you catch up, or maybe if you have an answer to that question. How can we incorporate a tissue fold in this layer. Yeah, so Clara's answer is maybe you could make the lambda value really high. That's a great answer. Absolutely. Another answer is you could change the target distance to 0. But so how should we approach this though? Do we change the target distance of all of this uniformly to either change the lambda distance, or do we change the target distance uniformly, or is there a strategy that we could adopt to sort of um, to sort of induce a fold? And the alternate question is, what would happen if we actually did it uniformly all over the tissue? Perfect. So Osman's answer is visiting certain locations using these statements. Clara's answer is, yeah, consecutively choose some neighbors. So those are the things we will actually be doing next, because all the focal point plasticity that we have, properties that we have initialized so far, are uniform throughout our tissue layer. So we need to induce some sort of asymmetry, asymmetry in this tissue, to be able to sort of induce these folds at particular locations. So if you want to just play with the simulation, the code should be under 7_3_2. So feel free to download that and run it. But if you are following along with this, I'm going to now walk you through how you can write it down in the steppable file. So we're going to break this piece of code into two parts. We're not going to incorporate those specific forces at every time step. We're going to pick up a particular simulation time. In this case, I've set it to 500. So we're basically letting the tissue relax for a bit, and then inducing these specific forces on the apical side. So our steps are going to be the same as we were following for building the links. So we're going to go through all of the apical cell compartments. But what we're now going to do is we're going to pick only cells which sit between particular positions on the x-axis. So in this case, I have picked up between 125 and 225, but feel free to sort of play around with the values that you want as well. And then what we're going to do is, once we have identified only those particular cells that are within this location, we're going to get all of their FPP links using the focal point plasticity dropdown, using the CC3D Python dropdown menu, and going to focal point plasticity, and then we're going to visit all links attached to a cell. So if you follow these 3 steps, you should be able to get all the links that a particular cell has at that point. Okay. And once we have those links for the cells that sit between those particular positions, we're going to increase the lambda distance, like many of you have pointed out. We could also do the target distance. We could also set the target distance to be pretty low, and so we can do a combination of both. And you can also choose to increase the lambda distance to a higher value and not do anything with the target distance either, and you should be able to see very similar effects. So to recap, these are the steps that we're following. We are choosing a particular simulation time. We are visiting all these cells of a particular kind, namely the apical, the cells over which we build our links. Then we're going to only cover particular positions on the x-axis, and I have some suggested values. Once we have identified these particular cells, we're going to find all the links that each cell is associated with. And then once we have that particular link, we're going to set the lambda distance to, say, 70, and then our target distance to 3. Remember, in our baseline simulation, our lambda distance was set at 10, and our target distance was set at 7, which is the width of the cell that we had picked. So now we're like messing around with these properties a bit. And so now, if you run the simulation, you should be able to see an output like this. So these are the cells particularly that we had picked out. And then once you have started, once you have changed the lambda distance and the target distance, because of the stronger forces that these cells are experiencing in the middle, what you'll be able to see is that these cells have sort of the apical sides of the cells have actually come closer together because you have properties set up that maintain the target size of each of these cells. Once the apical sides come closer together, you can see sort of the basal side sort of adopting this this fold, sort of like invaginating the tissue. You can add additional stuff to these to the simulation if you'd like. You could put internal links between the apical and basal that would put additional constraints on how strongly you want to maintain a cell shape. And so with those, you can have better control. But this feature use combining the Python XML, combining the steppable file, you're able to, at a particular point in time and spatial regions, you're able to manipulate the focal point plasticity parameters better. And so increasing the forces in a particular region allows you to sort of like build this fold in the tissue layer. I'm going to stop for a second and then check in with you. Are you able to produce the fold in the epithelium? Yeah. Anastasia, that looks great. I think some of these cells are coming off. So I don't know if you are already playing around with the higher target distances, but that's great to check out as well. So what are the values that will sort of keep the cell layer together? And those parameters will also depend upon sort of the simulation that you want and your cell volumes, etc. So I'm going to flash this slide on while the rest of you share more simulation outputs or are able to address any of these questions here. Our base simulation had a value of 10 and we increased it to 70. And you could also try playing around with that lambda distance values to see what other outputs you get. And the second question is, if you did, instead of picking up a small region, if you now, at that particular time point, just changed lambda distance for all the links uniformly, would you still expect that same behavior to occur? So maybe you could try this out while I address a question from Troy, who would like the Python codes back. So I'm going to go to this. And hopefully that's what you want to try. So let me quickly walk over what we had done. So we picked up a particular time point. We had picked up a particular region, after finding out all the apical cells and their associated lengths, we had increased the lambda distance, particularly for those lengths, and then we had tried to we had reduced the target distance between those cells. Okay. All right, so then I'm going to go back to the questions. So we have one answer which says that they would expect the cells to become squished and elongated because they would essentially try to maintain volume between serums. So yeah, there will definitely be cell shape changes there. But the other thing that'd be interesting is the whole folded shape that we're able to get in the middle is because of this asymmetry that you have put in the FPV properties. So if you changed all the properties at once, it would be it would also be a situation of the cells pulling on each other, and whichever gets there first will be able to pull neighboring cells closer to each other, but it would not give you an asymmetry at a particular region. Because all of these properties that you see would be uniform over the entire layer. So these sort of like asymmetries are important to create the folds in the tissue. Okay, so there is a request to go back to the code in the start section. So I'm going to do that right now. So in the start section, we did two different things. So we first made sure that the compartment cells know that they are part of a bigger cell body. And so we are using this function called reassign cluster ID to assign each cell to a general cell ID. So we have first looped over all the apical cells, then we have gone through each of the lateral cells. And then once we have identified that they were placed along the same region on the x-axis, and then we have reassigned the cluster IDs to the bigger apical cell cluster ID. And then we have done the same procedure for the basal. So this is the first thing we did. And then the other thing we did in this function was once we have reassigned the cluster IDs, we have looped over all the apical cells. Then we have identified if there are any common neighbors. If there is a neighbor, and if the neighbor is of the apical kind, then we have created a link between them using create FPP link. And the properties that we have set here are the lambda distance we have set here to 10, the target distance we have set here to 7, the maximum distance we have set to 200, which is not of an important parameter. Let me know if that helps. So we have a couple more outputs in the meantime. From Ashwarya to Harini, and it looks great. So now you can see the difference in a simulation with 30 versus right. So more answers on bending with 30 versus 70. So because the forces are not as strong, that you're not able to see a more pronounced fold in the tissue. And so again, so these are the parameters that you could use for your further simulations, depending on your biological context. And the anesthesia is a very nice output. That's great. It's exactly like you said. If you increase the target distance, so they're trying to maintain that higher target distance. And so, yeah, the cells have basically split apart because the lambda that you had put for those links was probably too high, and the internal contact energies could not keep the cell body together anymore. So with this, these were just to like give you a flavor of how you can play with some of the focal point plasticity parameters to to induce like these folds in the tissue. You can obviously build up upon this to create more complex simulations. I'm going to give you sort of some ideas of what we could do next. I think the main principles are also related to creating links, changing the properties, deleting links, maybe combining them with some plots that you would like to visualize. And hopefully those are the features that will be useful to you. We're going to study this in the context of inducing tissue breaks, and so more familiarly, a process of segmentation in which and you can break down an epithelium into discrete chunks. And that's what we're going to try to do, where once we're using the epithelial layer that we have built so far, we're going to play around with some of these focal point plasticity parameters to sort of like break these links at specific times, and so that we're able to see multiple folds in the tissue. And so if there are no other questions at this point, I can move on. I should say that the next three subsections, they are a little more Python heavy. So if you are not so familiar with coding as of yet, feel free to download these modules. I will walk you through what I have done, and you can, feel free to play around with the codes, and you can also reach out to me if there are any doubts. But I'm going to sort of not walk through every single line in the code right now, but give you the general overview of what we're trying to achieve. So there's also another question from Taylor. Are there any other ways to induce bending without altering links between cells? Changes in cell volume, for example, changes in cell volume. So yes, you might be able to do some of that, but the effects with just contact energies might not be very pronounced. You could possibly try more, even if you use things like elongation plugins, or if you even put FPP links, or yeah, like you have added like decreasing apical area, you will be able to do some of it. So the cell shape will definitely show changes, but if you want to make a more the FPP link and the use of these spring forces will be able to do a better job in that case. Okay, so the next thing we're going to do is sort of like understand how we can create this breakdown the epithelium into these discrete chunks. So yeah, if you download this code, it's under module 7_3_3. So what are the steps that we're going to do? So like I mentioned, a broader goal of this is also to be able to control the focal point plasticity parameters in space and time. And so what we want to do is, unlike the previous simulation, where we induced, the focal point, induced the changes at just a particular time point, we could also sort of incorporate it in the simulation as we go along. So we're going to use a couple of parameters, which I'm going to describe in the next slide in more detail. But the idea is that instead of saying that all cells should respond to these focal point plasticity parameters at the same time, we're going to incorporate that one by one. So what this is going to create is sort of like a wave-like pattern of contractility, if you see in this tissue. So you start off with roughly similar properties, and now you're sort of decreasing the target lengths or increasing the lambda distance between them, so that these cells on the left, which have already been, say, passed by that activation parameter, will start huddling closer together, while cells on the right side of the tissue, which has so far not seen that activation parameter, will be more or less symmetrical. And now as you keep, keep following the tissue, you can see, you can sort of like do this over time and indeed change these parameters more gradually. So there's a question, I'm not able to find these codes. So they should be, if you go to the student materials and demos, there should be a zip folder with module _7_3. There's another question on, would it be possible to connect the link strength to the pressure coming from overcrowding? I mean, to compress cells along the x-axis if there are too many? Absolutely. So that's the advantage of having all these properties in the steppable file, because you can, for example, for a particular cell, you can loop over, find how many numbers there are, what are their sizes, and then adjust focal point plasticity based on that readout. So yeah, you can absolutely connect, and all of these link properties are at the cellular level. So you can, sort of combine a lot of these different plugins to do what you want to do what you need to do biologically. Yeah. Okay. So sort of to be able to do this, we're going to need a couple of variables. And so in the simplest way, what we're going to use something which are the use of dictionaries. And I hope you have seen dictionaries before, but if not, it's a really valuable tool because, okay, thank you, Anastasia. So it's a really valuable tool because now you can connect a dictionary attribute to each cell, and that allows you to, keep tab of the feature across the simulation. So for example, at a particular time, say I have two neighboring cells, and one of them has seen that activation parameter already. So I can set that dictionary element, which I'm calling constrict, to be 1. But the nearby cell hasn't seen that activation parameter so far, so the constrict variable is still set to 0. And in the next time point, what's the next instance of that activation variable, both of these cells have now seen that constrict parameter. So both of them have been set to 1. And I can keep tab because each of these attributes are related to the individual cells. So for example, if I write a cell loop, I could check that for this particular cell, what does that constrict, dictionary attribute say? Is that 1 or 0? So based on this, when I'm able to do that, I can set up the following rules. If both of these dictionary attributes are set to, say, 1, I can allow changes between the focal point plasticity parameters from a baseline to something that changes. I can also make sure that I'm going sequentially down the epithelium column. So I can also keep track of making sure that if my neighbor to the right has been activated, only then make sure that you have changed the focal point plasticity parameters. So in this case, using this 3 parameters, this activation speed, say, or basically how fast you're able to activate individual cells, then looking at their individual dictionary attributes of constrict and, say, graph, and by the way, these could be any names that you pick for a simulation, I'm able to decide at what particular time and for which particular cell pairs I should change the focal plasticity parameters. Hopefully that makes sense. Please stop me if it doesn't. So now what I can do is the following. So if you have the module 7_3_3, the code for this that I have propped up on the screen should be in lines 74 to 80. So you can follow that along. By the way, I should mention, so because I wanted these codes to have greater Python flexibility, if you look at the start function of these codes, you might also see that I'm initializing a lot of the cell properties in the steppable file itself. And this helps me because I can now set up the number of cells I want. And while I'm initializing the cells, initialize the constrict, the graph, all of these dictionary attributes, or if I need to sort of like keep track of any other things, I can just do it in the Python steppable alone. And so if you compare the start functions of this particular module subsection, you might be able to see that it contains a lot more details. The goal is still the same. We're still trying to start off with a basic epithelium. We're still trying to build basic apical to apical links. But additionally, we also want to incorporate these dictionary attributes, so that also will be featured in the start function. Okay, so then once we have the start function ready, and now if you're following along this chunk of the code, which is in the steppable file at line 74 to 80, what you should be able to see is that there's that variable that I was telling you about, wave speed. So what we're saying is that every time you hit this wave speed, and I have used a modulo function here. Basically, what I'm saying is if it's a multiple of this wave speed, then this condition is satisfied. You can pick up your own condition here. But basically, once this time condition is met, say every 300 Monte Carlo steps or every 600 Monte Carlo steps, our goal will be to set apical cell with the constrict parameter to be 1. And the goal is also to make sure we know which position it lies along in the epithelial column. So this counter that I have just looped over the number of apical cells present lets me keep additional tab of which particular cell along the column has been activated. So this is all it's doing. So every time the simulation runs, and every time this condition is satisfied, it's activating that apical cell, and it's going step by step. So it activates cell to the left at one time point, then it goes to the cell on the right every time this condition is met. So where does this lead me? So So then what I can do is in the next following lines, and if you're following along on the Python code, that's in line number 82. So now I can loop over all the apical cells. Then whichever has been turned on by the constrict dictionary attributes, I can also investigate its following neighbor. So I first find out if it has itself been activated to start constricting. Then I look at its neighbor, and if the following neighbor has also been given the signal to go ahead and constrict, I can also additionally use that graph variable that I was telling you about to make sure that I'm comparing a cell to the right and then to the left, so that I'm not repeating the loop multiple times. Once these conditions have been met, I'm doing the same thing that I was doing before, where I can manipulate the lambda distance properties, and I can also do similar things with the target distance. In this case, I haven't played around with it, but feel free to do so. The other thing that we could also do is, like, rather setting it to, like, just one step increase in the lambda distance, we can also, like, increase it slowly so that you can slowly start seeing the cells come closer to each other, and that also gives time to adjacent cells which have not been activated yet to sort of like adjust its body to still maintain that epithelium. So far, just to sum it up, what I've done is in this new version, to be able to control some of these properties better in time, we have identified sort of like 3 variables. One which during the course of the simulation at every couple of Monte Carlo steps gives a cell signal to be able to constrict. That's the wave speed parameter. Once that wave speed parameter has been reached, we're using two dictionary variables called constrict and graph to just keep tab of the fact that that cell has the ability now to constrict. And the graph parameter additionally lets us, make sure that we are doing this loop only once, so that we are following a cell to the left and then the immediate one to its right. And then once we have identified all of these cell pairs, we have gone through our apical loop again. We have tried to find out if a cell and its neighbor both have been given the signal, and then we're slowly increasing the lambda distance. And so with this, if you now sort of run the simulation, you should be able to see shapes like these. So let me know if you have if you're able to produce this output, if this makes sense, or if this raises any additional questions that you'd like to ask me. So then let me tell you why this is helpful. So we're going to use one of the features that has emerged by the sequential activation of focal point plasticity parameters, which is that if you look at some of these cells which have just been activated, they are in a better state to be able to change their position and follow, start changing their focal adhesion parameters, focal plasticity parameters. Whereas cells on the left side of the simulation, they are, stuck in a very hard position because they are, the lambda distance for them has increased a lot to this point, but there are groups of cells on either side, so they're not able to sort of achieve what their target parameters have been. So we will be exploiting this in a second to sort of say that if a cell which is way too far from reaching their target parameters, if it's not able to achieve the target parameters, that link should just break. And we're going to sort of try to see where the positions of these breaks occur. And we could even ask how regular these breaks are so that it could mimic the sort of segmentation, the segmentation images that I was showing you earlier. So there is a question from Anastasia on explaining the line, which would be line number 80 if you're looking at module 7_3_3. So yeah, so in this simulation, the additional thing I had to do was put two fixed cells on either side of the simulation, because if we still had the periodic cells which could loop around and tie together, you would not be able to sort of constrict the you would not be able to induce the levels of stress that these cells are experiencing, because the whole tissue would just keep moving along. So I have two fixed cells at the end of the simulation. Because I had placed these two fixed cells, starting from x position equal to 0 to the end of the simulation, they also have IDs of 1 to n, where n is the number of cells. So what the simulation is essentially doing is saying that just ignore those two fixed cells at the end and only start incorporating the focal point plasticity from the second parameter, from the second cell. And so that the thing which you see is len self IDs -2 is saying that stop before it reaches the second last cell, because that last cell is fixed and you're not going to be able to move them. And also you're starting it from the first counter. So it's just to be able to meet these fixed boundary conditions. Depending on our simulation, you might not need these kind of cells, or you might have other criteria. There are also ways to put wall-like cells in CompuCell, and basically the idea is that you could put a separate cell type which has a very high lambda, associated to the volume plugin, and so essentially that makes them very stiff. So you could also do things like that, and yeah. Okay, so then we are going to be using we're going to use the fact that some of these cells are in a more stressed state where they're not able to meet their uh, target FPP parameters. And you could also see these cells, they get a little elongated because they're trying very hard to match that distance between the apical to apical compartments. And so they're basically like pushing the cell, pushing their cell body to be able to achieve that. So what we're going to do next is we're going to go back to our go back to our steppable file. And the code for this is under 7_3_4. And let me tell you the line numbers quickly. So if you look at line numbers 94 to 100, that's where we have made the rest of these changes. So our first check was we have already, no, we had already checked uh, if they fulfill the constriction rules, then start by bringing them closer together. Now we're going to do one additional check. For a given cell pair, we are also going to find out what is the actual cell distance that separates them. So we're going to just use a basic center of mass to center of mass Euclidean distance, where for two corresponding neighboring cells, we're going to find out what is the actual distance they have been able to achieve. And we're also going to multiply this target distance with the lambda that is basically set for that cell pair. Now, this combination, the lambda that they're supposed to reach and the deviation from what they were supposed to reach in their apical to apical distances, gives us an estimate of how stressed that cell is at not being able to match its required target distance. And so what we can do in the simplest cases, we can set off a cutoff. In this case, I've set it to 400, and you could play around it in the simulation to see. What I've said is if that value of unhappiness for that cell pair at not being able to match the focal point plasticity parameters is greater than 100, just add it to a list, and any cell pair that's in this list, we're just going to delete that particular link between the pair. And the following deletion, if you want, that's just following this loop. So in the code, it's under lines 104 to 109. So this chunk only adds the particular cells to be deleted, and you can delete it later in a different loop. I recommend if in the future you're interested in like deletions, I recommend that's the way to go, because if you keep finding out the cell pairs and deleting them in the same loop, then that might create like a conflict of which links exist versus not. So it's a better idea to just save all the things that you want to be deleted and then doing it later. And then the deletion parameters should be under the same FPP window. It's called delete FPP link, which I've written down here. You should also be able to see it in the code snippet. All right, so now what happens is once you delete those particular links of the stressed cells, you should be able to see a pattern emerging in the tissue where you have this activation parameter that progresses down from the left to the right side of the tissue, allowing cells to constrict their distances. But as the cells depending on where that cell pair is from that activation parameter, or which cell has been reached by that activation parameter, you'll be able to see that if you delete certain link pairs, you can see these like folds that emerge in the tissue now. And so this is sort of like one way that you could incorporate changes in the focal point plasticity parameter in like space and time to make it more suitable for the needs that you want. In my case, I was also very interested in understanding how symmetrical these different breaks are. So the next put down a small exercise for you if it helps for you to just add add these features to plots. So for example, you can try finding the locations at which these breaks occur, and then by comparing positions of these breaks, you can start to see how uniform or how uniform or non-uniform these break locations are. If you want the solution, the plots are with the plots added. That's in module 7_3_5. So feel free to check that out. I will pause here for a second to see if anybody has actually played with the code, and if you are trying to change the tension, which is in line number, depending on. If you go to module 7_3_4, that's on line number 99. So if you play with that parameter, 9900. So if you play with that parameter from 250 to 500, let me know what you see. And I'm going to stop here for a minute. But this is the main crux of what I had to show you. I hope this gives you a little bit more information on how to use the Focal Point Plasticity plugin. But yeah, feel free to play around with these two values. Nice. So Troy has an answer on that the apical islands are longer at 500, right? So based on this, so what we have essentially said, like given them a little bit more room to say that only when their tension thresholds are greater than 500, then break. And so that allows allows the cell clusters to become a little bigger. And you could try going the other way too, to decrease it to say 250, and you should be able to see you'd be able to see the opposite happening as well. Are there any other questions regarding the FED plugins or anything else I can help answer? I'm just going to go to the end of the module. And like I said, if you have any other questions regarding the Focal Point Plasticity plugin or any of these codes, I'm happy to answer. Thanks so much, everyone.